So I'd like to welcome everyone to today's HPC Best Practices webinar. Today's webinar is from Damian Rouson at Berkeley Lab, and he'll tell us about some of the capabilities that you might not be so familiar with in more recent versions of Fortran, and can be quite beneficial in writing succinct and correct code. So as always in this webinar series, we'd like to encourage questions as we go along. We have a Google Doc, and the link is there on the screen, but I'll also be putting it in the chat periodically during the session. We encourage you to ask questions there, and this will give also Damian an opportunity after the fact to answer any questions that we don't have time to cover during the webinar. I'll try to keep an eye on the chat and transfer questions from there as I can, but sometimes it gets a little busy. We'd also very much appreciate your feedback on this and all webinars in our series, and there's a link for that. Just a couple of questions in a simple Google form, and I'll put that also in the chat as we go along. As with all of the webinars in this series, we will be posting the recording, the slides, the Q&A notes. And if you registered, you'll receive an email when those are posted, and you're welcome to share them with others. Otherwise, you can go to the website that hosts the webinar series, and the instructions are there, and you can keep an eye on the event page for this webinar for it to be updated with results. And now I'll turn it over to Damian. Thanks.
Okay, thanks, David, and thanks for the invitation. And I will share my screen and that's the whole screen. Let's do just the keynote window. Okay, hopefully you guys can see my screen. And I'll reiterate what David said, which is that I'm quite happy to take questions along the way. I remember during the pandemic when I first gave a remote talk, and one of the most awkward things is telling a joke and not having any idea if it landed because everyone's muted and has their cameras off. So some interaction during the talk is actually great. So please jump in as you like. So my title, of course, is intended to be a little bit provocative. Please, no more loops than necessary. Of course, some loops are necessary, but the main point is that loops are inherently sequential and verbose, and we have better technologies and have had better technologies for quite some time. So as David said, I'm Damian Rouson. I'm the group lead for computer languages and system software at Berkeley Lab. And I have the URL here for the Fortran team at Berkeley Lab. In my group, we like to start with our acknowledgements. And there are a lot of people who I develop open source software with, many of whom, those who I've worked most closely with, you can see in this acknowledgement. And several of the packages that are listed here, Julienne, Fiats, Formal, will play a role in this talk. This work is sponsored by DOE and used resources at NERSC Supercomputer Center. So first, some background. We're going to go deep here, right back to the beginning of Fortran, which was the first widely used programming language. So in some sense, the beginning of widely used high-level programming languages. And then talk about various features that came into the language through various standards. David asked me initially to talk about new features and recent standards. I asked if I could go a little bit further back. Probably most of you don't think of 35 years ago as recent, but there are a number of features that are really useful, particularly on the theme of writing more compact code, higher performing code, all the way back to Fortran 90. So I'm going to cover the standard starting with Fortran 90, and even talk a little bit about a preview of what the Fortran Standard Committee calls Fortran 22Y, where I believe Y is likely to be an 8, so it'll probably be Fortran 2028. And then we'll get into some use cases, talk about the software packages that I just listed, and really dive into some of the nooks and crannies that I think are oftentimes underlooked, but also what I'm calling vast pastures that are big open areas of the language that generally get overlooked. And finally, some concluding thoughts. So 1956 was the first Fortran manual. Originally, it was an IBM product, and the team that developed Fortran was led by John Bacchus. And this image of the cover of that manual is from the Wikipedia page. So I had actually seen this numerous times, but it wasn't until this past October I was giving a keynote at the International Workshop on OpenMP when I decided to look up the full manual, see if I could find it. And it was really fascinating and fits right into the theme of this talk. because on the very first page of the very first chapter, it talks about loops. It talks about do loops. And so the point that I'd like to make, I'd really like to stick with everyone, is that when you're writing a loop, you are using a 70-year-old technology. So if your loop were a person, your loop qualifies for Medicare. Depending on where your loop's birthday falls in the year, your loop would be qualify for full Social Security benefits. So this is really old stuff, and there are more compact and potentially higher performing ways to write code, and so that's what I'd like to show you. So let's take a step through the standards, starting with Fortran 90. So what I'm listing here is not completely comprehensive, but the majority of the features that entered the standard. And what I'm going to do is, so a lot of the features that are in a white font are features that many people, at least if you're a Fortran programmer, are already familiar with. And unfortunately, you can see how long this list is. It's not going to be possible for me to go into detailed definitions of each feature. What I really want to do is focus on the things that I think people are missing. And in that regard, I have some that are in a red font. So for example, defined operations. This is the ability to not only overload the existing operators in the language, but also to define new operators. And we'll see where that can be put to great effect in some of the software that we develop. Also, array statements, which are one of the ways that I'm going to show that you can help to get around having to write loops. Structure constructors, I won't have a chance to talk about much in the talk, so I'll just say if you have a derived type, the language gives you a structure constructor, a way to invoke what looks like a function, but basically in one line you can initialize all the components of that object, and that's what structure constructors are for. And intrinsic functions, of course, people are familiar with many of the intrinsic functions in the language, sine, cosine, things like that, but there's a much longer list than most people would likely be familiar with, and they can be used to write very compact, advanced, sophisticated code. These features I'm grouping into the various programming paradigms. Fortran really is a multi-paradigm language now. So starting with Fortran 90, you could do what some would call object-based programming. I've seen a couple of different definitions of that. Usually object-based programming is sort of object-oriented programming minus whatever you think is the most important part of object-oriented programming, which typically is inheritance. And so what we're missing in Fortran 90 is the ability to define a child class that inherits state and behavior from a parent class or derived type. Then there's not a lot in the language that really explicitly targets functional programming, but there are some features that I've sort of hijacked for that purpose. And functional programming oftentimes involves a lot of recursions. That's why I have that listed there. And really the array programming is one of the areas that Fortran, I think, stands out and gives you the ability to do some things that a lot of people aren't really taking advantage of. There's modules, groupings of code into scopes. Fortran doesn't have a file scope, so the way that you scope things is with modules and submodules. And then structured programming, that's sort of old news, but just a better way to write loops. And then Fortran 95. And when I see this slide, I always think of a postdoc that I was collaborating with recently who was born in 1995 and said to me during a call, I've looked at it. I don't really think I need anything beyond Fortran 95. And I replied, that could only be true if you think the Fortran committee has wasted your entire lifetime. And within 5 minutes, the postdoc asked me a question for which the answer was a 2008 feature. We wanted to know if elemental procedures could be impure. And Fortran 2008 added the ability for a procedure to be impure. And this person writes very sophisticated MPI. So I asked if he was using the MPI F08 module, which is a more modern way to use MPI from Fortran. And he said yes. And the MPI F08 module is actually misnamed because it's using features, it's enabled by features in Fortran 2018. So right off the bat within the same call, I was able to explain how a feature from Fortran 2008 was useful and 2018 was useful under the hood without the postdoc knowing it. So we do have the ability to declare procedures that are pure, meaning side effect free. So they don't modify their arguments, they don't do things like IO. And so that is maybe the one area in which the language is explicitly enabling functional programming. And the elemental is going to play a pretty big role here. The basic idea with elemental procedures is that you write a procedure as if all of its arguments are scalars, but then the client code can actually call the procedure passing in arrays. And the compiler will simply apply that procedure to, let's say it's a function and that gives a result. the compiler will apply that function to every element of the array and then give you an array result back. And Fortran 2003 is the first version of the language that really went fully object-oriented. So now we have type extension, which is our term for inheritance, and the ability to define type-bound procedures. For C++ programmer, that's like a virtual member function, essentially. We have runtime polymorphism. Final subroutines are like destructors in C++, if you're more familiar with that language. But what I'd like to focus on is kind of a baby step that the language took towards generic programming, parameterized derived types. So the ability to define a type that has either a kind parameter or a length parameter on it. And you can use that kind parameter to set things like the precision or the character set or things like that. And there's a much bigger step towards generic programming coming down the road that I'll talk about in a moment. I won't have a time to show anything with vector subscripts, but the basic idea is for your subscript for an array, you can drop in a one-dimensional array that has essentially a list of subscripts. So now you're indexing through the array in one line and grabbing a bunch of elements and doing some manipulation on them instead of having to write a loop. Abstract types, I won't play a role in this talk, but I'd say as I began to get into object-oriented design patterns, I found that was kind of a common theme. Oftentimes what is described as a pattern is just a good use of abstract types. And the associate construct is one of the features that I've sort of hijacked for functional programming style. Functional programming emphasizes immutable state. And so the common practice is declare and then later define. And that's problematic in the sense that every line between the declaration and the point where you define it, that variable is undefined, which means if you accidentally use it, that's going to be a bug. What associate does is if you associate with an expression, at least in that case, you give it a name that then is immutable. And so I use that feature a lot more than you'll see in most codes. Fortran 2008 is what took the language parallel. And also the committee designed a feature, the do concurrent construct that with GPUs in mind. I've been on the Fortran committee since about 2013. This actually took place before I joined the committee, but the basic idea that the former lead of the US body within the Fortran committee, Dan Nagel, said to me, give the programmer the ability to communicate properties of their code, like these iterations can be done in any order, including in parallel, rather than mandating specific optimizations like vectorization, multi-threading, offloading. And so that's what do concurrent is doing for you. You also have the ability to launch multiple images. If you're an MPI programmer, think of launching multiple ranks. And so it's a single program, multiple data, SPMD style programming, just like you have with MPI. And you have a partitioned global address space, which are co-arrays, basically distributed data structures that you can use. And this is all part of the language. And again, this is in red because it's really overlooked. A lot of people aren't using it. They're leaving both a savings in compactness on the table, also robustness, because in a lot of ways this is simpler than a lot of the MPI that people are writing, and even leaving performance on the table. The vast majority of codes that are writing MPI are using two-sided communication, sends and receives. They would typically get better performance by switching to one-sided communication, puts and gets, but that's much harder to write. So it's probably better to switch to a technology that's built into your language that does one-sided communication for you. And that's what Fortran's parallel programming feature set does. Pointer rank remapping basically says I can take an array of any rank. We use rank in Fortran to define the dimension of an array, that how many subscripts an array has. So I could take a two-dimensional array, but I could associate a one-dimensional pointer with it, and then I could index through it as if it were a one-dimensional array. And submodules. This is something, again, I won't have time to go into. I'd love to come back and give another talk at some point and maybe go over some of these things that I can't touch on. But submodules, even though I don't have them in this talk, are absolutely essential for the work that I do. And that is because I spend a lot of time submitting compiler bug reports. Since the beginning of 2024, nonstop, I've averaged about one compiler bug report a week. I will say, however, of all of those bugs, only one that I recall was on flang, and that was just submitted a week or two ago. And the reason submodules are so important in that setting is that in order to get a compiler team to respond to your bug report, you really need to submit a small reproducer. And with the approach that I use, where modules, if you're a C++ programmer, the way I use modules, you can think of them kind of like a header file. So I have function interface bodies, is what Fortran calls them, or what you'd call a function prototype. And I put that in the module, and then I put the procedure definition in the submodule. What ends up happening is that my submodules are always leaf nodes. And so that means that if I'm trying to reduce 10,000 lines of code to a 25-line reproducer, if I get a compile time error in a module, for example, bam, right away, the first thing I can do is remove all of my submodules um, because they're leaf nodes. And that has lots of implications also just conceptually in terms of being able to trace through code. So Fortran 2018, the language took really two big leaps forward. I'm putting C interoperability here in parentheses because I don't know that I would call it a programming paradigm. But the idea is that there were some features I skipped over in 2003 that made Fortran interoperable with C, meaning you can basically declare types in Fortran that are effectively C types and pass them around as native Fortran types. And that feature set got expanded greatly in Fortran 2018, so that now you can also call functions to manipulate Fortran objects in C in a standard conforming way. What I'll focus on more closely is the parallel programming feature set, things like collective subroutines, so you can do broadcasts across images. All this stuff, by the way, works both in shared memory and also in distributed memory. And events are encapsulated atomics that you can use as semaphores for coordination across images. Locality specifiers for do concurrent give you the ability to specify that a variable is local to a given iteration or shared across iterations. And you're probably used to almost all modern Fortran programmers are putting implicit none in all of their scopes. And as Bill Long, who retired from HPE, once said, default none is good code hygiene. Basically, it's like implicit none. It's saying it's telling the compiler, I'm going to declare the locality of each of the variables that are accessed inside this do concurrent construct, and the compiler then is obligated to police me on that. We have teams, which are collections of images, and some ability for fault tolerance to basically be able to detect if an image is no longer responding. Fortran 2023 is the current standard, and we've added a locality specifier called reduce, and I'll show you where we make use of that in the deep learning library that we develop, and what I'm calling put notifications, the ability for one image to put data on another image, and in one instruction, one statement, notify the other image that the data is there and ready for use. You can now make lines as long as you want, up to 1 million characters, and so I often, when I guess I've probably said modern Fortran several times already today. Usually, I just substitute whatever's the latest standard instead of saying modern Fortran, and that's because Fortran is largely backwards compatible. And in this case, if you're writing any statement that is more than 132 columns long, you're writing Fortran 2023. So I basically just call all modern Fortran 2023 or whatever the latest standard is. Even if you're doing something that simple, you're taking advantage of the Fortran 2023 standard. And as I mentioned, upcoming is Fortran 22Y. And I think the most impactful thing that's coming there, or the biggest feature set, is the generic programming. And I'll talk about how that can be really useful in some of the coming slides on use cases. I lead the HPC subgroup for the Fortran committee, and with a lot of great help from my group members, Kate Rasmussen and Dan Benachea. We're doing a lot of things on the committee to enhance the operations of the committee, but also to expand the parallel features to improve the support for high performance programming. So things like team collectives, being able to do a collective that just works within a given team of images, and asynchronous collectives, so that you'll be able to launch a collective, return without having the result of that collective, and then later check to see if the result is there. Okay, nooks and crannies. It's funny, we use these terms that maybe we never actually look up. So I just thought, since I'm using this term, I had to look up what I'm talking about here. It turns out cranny is actually just a synonym for nook. So we're kind of saying the same thing twice, but think of a little space where you go to read. And what I like about this image is that it is a little space and on the side of a room, but you've also got these books there, and those contain new worlds. They're vast universes of thought. And so that's kind of the idea here, is that is that we sort of have both things that I think people are missing from the language. Some of these little features that would be really useful, but also some really, really big feature sets. The little things that I would say are really useful, for example, this is the list of intrinsic procedures, intrinsic functions in the language. And it's not very easy to read the standard, so I don't necessarily recommend that as a way to learn Fortran or probably any standard language. But what I do recommend that everyone do is get familiar with the intrinsic functions. It's a much longer list than you might imagine. I won't have time for it today, but we have one great example where in one of the software packages that we develop, we've got two statements that if you took that statement and expanded it into the way most people would write code, including loops and explicit allocations and things like that, but also maybe someone who doesn't know all the intrinsic functions. And those two statements expand into, I think it was 37 lines of code. So if you take advantage of the features of the language, you can write much more compact code. And you can also then offload a lot of logic to the compiler. And hopefully the compiler developers know more than we do about how to optimize that algorithm, and at least in many cases. Expansive pastures. I thought this might be a good picture to show, given the big events at the World Economic Forum in Davos right now. This is a picture that I took on the way to the PASC 23 conference, which in 2023 was in Davos, Switzerland. So the expansive pastures are the big parts of the language that really a lot of people are overlooking. And this in no way is intended for you to read every word in this slide. What it's actually intended to do is to come at you with overwhelming force and convince you that the parallel programming features in Fortran are significant, numerous, massive, and yet very, very much underutilized. And as I mentioned, you would benefit in terms of, in many regrets, robustness, performance, compactness. And so this is an area of the language that I recommend that people start to take more of a look at as well. So where are these nooks and crannies and pastures in the software that we write? I'll give you a few examples. Start with Julienne. So Julienne is a correctness checking framework. And the name was inspired by a package called Veggies that's developed by Brad Richardson. He used to work here at Berkeley Lab and now works for NASA. And I was having some trouble with portability for Veggies. There was one compiler that couldn't compile Veggies, and that compiler was very important to me. And so I decided to write a tiny utility just as a temporary replacement. But as time went on, that utility took on a life of its own, and we started to add some features that I think now make it compelling in its own right. And so you can use Julienne for writing unit tests, and you can also use, which are basically external checks of code, or you can use Julienne for writing assertions, which are basically internal checks in code. And Julienne embraces the features of parallelism that are part of Fortran. So, and we have some thoughts and plans around supporting MPI code. I don't think it would be that hard, but for now, there's very few packages out there that explicitly support the parallel features that are in Fortran, and so that's the market that we're targeting initially. So, for example, you can do multi-image testing, so running parallel tests, and we use a collective reduction to detect failure on any subset of images. Could be one image. If a test fails on one image, then we report a failure. And the assertions that we provide are pure procedures. This is really important for a couple of reasons. One is that not many people write pure procedures, and one of the more common reasons I hear for why people don't write pure procedures is because you're not allowed to do I/O, which means they can't print when they're debugging code. And so one philosophy, and this philosophy doesn't necessarily address all of the world's problems, but one philosophy is assert what you expect to be true, and our assertion utility will check that for you. The one way you can do output in an assertion procedure is with error termination. The basic philosophy is once we're at the point of deciding that there's an error in the code and we have to stop, all bets are off on things like the performance that pure can gain you. And so there's an error stop statement in the language that can have either an integer stop code or a character stop code. We basically hijack that feature to give you rich data about what went wrong inside that character stop code, inside that string, basically. And so you can use our assertions inside pure procedures, which helps with debugging. Also helps with performance in the sense that one of the constraints in the language is that any procedure you call inside do concurrent must be pure. And so our assertions can be, so having our assertions pure means that they can be used inside do concurrent. Highlighting here just that the software that I'm going to show you is typically, all or very nearly all Fortran code. And that's even true for the software that we're using to build our code that I'll show you towards the end if we have a moment. This is the Fortran Package Manager, FPM. So Julienne defines idioms. And this sort of came about partly because about maybe 10 years back, I ran across the term idiomatic Python. And I was a little bit jealous. I thought, I want to like have an idiomatic Fortran. But then the problem is, well, who am I to define what idiomatic Fortran is, or what's the natural way to use Fortran? But then as I was working on this feature in Julienne, it suddenly dawned on me that I was defining idioms. So this is idiomatic Fortran, quite literally. And the basic idea is that defined operations I mentioned earlier are user-defined operators. Here in this table, we're showing the operators that Julienne provides in bold. In Fortran, when you define your own operator, you bracket it with dots. So approximates is an operator and within is an operator here. So we're giving you the ability to write what effectively is a natural language sentence in standard conforming Fortran syntax. And it does exactly what you might imagine. If you write X approximates Y within tolerance, Julienne's going to check the difference between X and Y, take the absolute value, and see if it's less than the tolerance that you've given. Now, here's the really significant thing, getting back to an underutilized feature. Most of the operators in Julienne are elemental. So remember earlier I said that you write the procedure as if the arguments are scalars. So probably when you read that first line in this table, you might be thinking of X and Y as scalars, but they could actually also be arrays. In fact, they could be one-dimensional, two-dimensional, all the way out to the maximum, which is 15 dimensions for an array, rank 15. And so if you think about the implications of that in terms of code compactness and robustness, the compiler, instead of me having to write a loop over all the elements of that array, which means that when I talk about robustness, there's a possibility of going outside of the bounds of the array. Instead, by letting the compiler do it, there's no possibility of that unless there's a compiler bug. But also, it makes the code really compact. So if you think about binary operators, like approximates and within are binary or less than, in some cases here, you might think, okay, less than, why not just overload the existing operator? But there's some times where it gets confusing to look at code where you're not quite sure whether you're looking at a defined operation or an intrinsic operator. So even for the ones where we could overload an existing operator, we typically don't. But also because we have the ability to then do a lot more inside that operator, so that if you have a big array and only say one or two elements fail, we're going to give you a diagnostic message only about those elements that failed. And all of that gets handled automatically inside Julienne. Also importantly, in terms of compactness, these binary operators, when they're elemental, they can take any conformable operands. So operands are conformable if they're arrays that have the same shape, or a combination of a scalar and an array are also conformable. And so what that means then is we get to write one elemental function that works on scalars. That function defines the operator and accepts 46 combinations of operands. One for the case if they're scalars, 15 for the case where they're same-shaped arrays, and they could be of rank 1 through 15, or 30 for the case where it's a scalar array combination in either order. So that means we write one function once, just working on scalars, so we're not doing any loops over, array dimensions, and effectively it's like the compiler generates the other 45 cases of that function for us automatically. So it's a tremendous savings in the in code complexity. I guess you could imagine there's a factor of 46 expansion if you had to do all of this stuff without elemental procedures. So I think it's a pretty big deal. This is the newest kit on the block. This is a package that was just approved for public release by Berkeley Lab last week, and it's called Formal. And it's a package that I'm developing in collaboration with Jose Castillo at San Diego State University, who works on what he calls mimetic discretizations. Mimetic discretizations are methods that for defining a discrete calculus to work on tensor field quantities, scalar fields, vector fields, things like that, and define discrete differential and integral operators that mimic continuous operators in their behavior, meaning, for example, they satisfy certain important theorems like Gauss's divergence theorem. And so what we have in formal so far is based on a paper from Corbino and Castillo from 2020. Johnny Corbino, the first author there, was also a member of my group a couple years back and now works at Siemens. And we're at the early stages of this. It's about 3,000 lines of code just written this past fall. Right now, it works on one-dimensional problems nominally, although in some sense, the universe is always one-dimensional, always three-dimensional, or four if you're into general relativity. And when you're working along one dimension, what you're really doing is solving a problem where there's no variation in the other two dimensions, which means most of your quantities are basically per unit area of the other two dimensions. So one nice thing also about mimetic discretizations as defined by Corbino and Castillo is that once you've defined the 1D operators, there's then a set of transformations that directly get you the 2D and 3D operators for things like divergence and gradient using a Kronecker product involving where one of the operands in the product is the 1D operator. So it should be straightforward. I expect to start working on 2D and 3D discretizations very soon, hopefully no later than next month. And so where is this stuff headed? It's not just about defining these abstractions, but down the road, turning this into an embedded domain-specific language, a DSL for tensor calculus. There's also some implications for formal verification by leveraging a technique that my collaborator Magne Havidon at the University of Bergen in Norway refers to as proof by testing, or what I would call problem-specific proof by testing. I'll talk about that more in a little bit. And of course, when you see the word tensor these days, the first thing that comes to mind is machine learning. So right now we're focused on computational physics, but we should be able to apply a lot of what we're doing also to tensor contractions for machine learning. So formal stands for Fortran Mimetic Abstraction Language, where Jose and his collaborators have been working on numerical methods to define discrete operators that mimic continuous operators. For a long time, I've been working on software abstractions that mimic the same continuous operators and continuous fields. And so hence the name. So just to give you an example of what I'm talking about, if you clone formal and run one of the examples in the repository, it's checking what Jose refers to as the extended Gauss divergence theorem. You might be used to seeing the Gauss, the second plus sign here should be an equal sign. You might be used to seeing the Gauss divergence theorem with two terms, where basically you have a volume integral on one side and a surface integral on the other side. And if you are, and then in the integrand then is the divergence of a vector field, excuse me. If you think of that vector field as the product of a scalar and a second vector field, then you can basically use the product rule to expand that volume integral into two terms. And that's how you get here what's called the extended Gauss divergence theorem. And if you run this example using the Fortran package manager in formal, and the example has some a function here that's used to initialize a scalar quantity f, and a function that's used to initialize a vector quantity. And you can also go in and change to much more complicated functions, and we still tend to get good results. I like this result especially because we're getting, we're lucky enough that in this case, I guess because it's a fourth order method and we're only using, at most second order polynomials, we're literally getting, exact answers, I guess, almost down to the last digit. And so you see the notation here, which hopefully you can tell is attempting to mimic the notation that you would have if you were writing this in a textbook, or a paper using LaTeX. And so these are all operators that are defined inside formal. And so I'm using a triple S to represent a triple integral and a double S to represent a double integral, and then just checking the satisfaction of the extended Gauss divergence theorem for these functions. And again, just in 1D for now. So I mentioned Magne Havidon. He is a language designer and also teaches formal methods at the University of Bergen. And he made a comment that was really impactful for me just a couple months back when he said, when you're writing type-safe templates, so this is the new technology that's coming up at the next Fortran standard. One of the points I'd like to make in this talk is that we oftentimes think of Fortran as a legacy language, or like when we hear legacy code, Fortran is usually one of the first things that comes to mind. But in reality, each language is ahead of or behind the other languages because they're diverging. They're developing capabilities that many times the others don't have. For example, with co-arrays, I mentioned that you can run a distributed memory just with Fortran features, no MPI anywhere in your code. And so oftentimes what happens is if we're not ahead in an area, the committee doesn't just try to adopt a technology, it tries to take a view of how has that technology worked out in practice in these other languages and what can we do better. So sometimes we leapfrog other languages. So yes, we're late to the game in bringing templates. We were ahead of the game in other ways, but we're not just bringing in templates, we're bringing in a powerful feature called requirements that I'll talk about in a moment that enables you to write type-safe templates. And that's something I'm not aware of in other languages. Certainly, it's not the case in C++. And by the way, I'll also just mention, when I talked about modules earlier, C++ now has modules, and Brad King at Kitware, who I've known for many years, was the main person, I believe, behind proposing that feature for C++. And I know for sure that he was inspired by the Fortran feature. And so this again is where languages sort of leapfrog and play catch up. And Magna Haviduen also collaborates with Bjarne Stroustrup, I don't know if I pronounced the last name correctly, but he's the inventor of C++. And Bjarne recently told Magna, now that I have modules, I almost don't need header files anymore. So again, depending on what features of the language you're using, either language can be thought of as ahead of or behind the other language. We were way ahead on modules, way ahead on distributed memory programming, things like that. So Magnus says that when you're writing type-safe templates, you can consider the requirements as defining a DSL for the template body. Such DSLs are extremely cheap to define, just a collection of derived declarations and have no runtime overhead. So, the derived type declarations he's talking about are the kinds of things I was just, or at least informal, are the things I was just talking about, like a scalar and a vector and things like that. And so this is what requirements will look like in templates in Fortran. I borrowed this slide from Tom Clooney, who's also on the Fortran committee and works at NASA Goddard. And the basic idea here is that I tell the compiler that I'm going to write an algorithm in my template generically, and it's going to require an operator. That operator is going to be defined by a function. That function is going to take 2 arguments, so it's a binary operator. And I'm going to refer to the type of the left-hand operand as T and the type of the right-hand operand as U, but those are deferred types. Those are not actual specific concrete types anywhere in my code. And I'm going to refer to the result as being of type V. Now, what that means is the compiler can check various things. I'm going to use those requirements inside my template body, and the compiler will be able to see, hey, wait a minute, you added a T and a U, and you're trying to assign it to a W type. That doesn't work. So it can do type checking generically inside your algorithm in your template. This is the really powerful technology, both in terms of things like, somebody might need to mute. I thought I heard a question. So it's a really powerful technology, both for practical reasons, because you'll get error messages in your template, not in generated code that you didn't write, and not even at the point of instantiation, but right in the template that you're writing. And also powerful in terms of the implications that it has for formal verification. One of the points that Magna makes is that when we're talking about stencil calculations, like the tensor calculus calculations I talked about a moment ago, we generally think of these in practice and for scientific use as floating point calculations, but because you have the algorithm templated, you can switch to integers, and now you can do exact math. And you don't, and what happens is, as Magna puts it, the type-safe templates gets you almost all the way to a formal proof of correctness, and you can actually get over the finish line to a formal proof of correctness in a problem-specific way, with a finite set of integer tests on your template algorithm. And the basic idea there is that I don't necessarily care if every stencil calculation, for example, could be thought of as a matrix calculation. So if I'm doing differentiation, it's a matrix vector multiply. I don't necessarily care that this code is correct for every possible stencil or every possible size of my grid. But if I know the size of the grid that I'm going to work on, and if I know the grid that I'm going to work on, and if I can delineate the possible ways this algorithm could go wrong, like maybe I flipped indices, and if I can show that none of those are happening, then I can actually prove that for my problem, this code is correct. So the other reason for the name formal is that we believe, and this is a research subject, we believe that this will lead towards formal verification of practical code for science. And I think that also has important implications for AI. For AI assisted code, I often say one of the problems is the code doesn't come with a proof of correctness. Well, now you might be able to write or at least complete your own proof of correctness just with your tests if this problem-specific proof by testing approach works out. We do work in deep learning, and so we develop a library called Fiats, functional inference and training for surrogates. If you're amongst friends, you can also refer to it as Fortran inference and training for science. We don't always say the word Fortran. I notice a lot of computational scientists don't talk about their code if they're writing Fortran because it's sort of the language that gets looked down upon the most. And so, two ways to expand that acronym. Also, a fiat is a declaration from a dictator. And I actually think that the name then is sort of a cautionary tale on we need to be careful about the answers that we get from the AI models that we're using. And so one of the things about Fiats that makes it unique, besides the fact that it is Fortran all the way down, we're not making any calls into external libraries like PyTorch or TensorFlow, and also all of the inference procedures and the training procedures are pure, which means you can use them inside do concurrent, which means you can multi-thread or parallelize your inference batch inference automatically, or even offload it to a GPU. And that's really significant because if you're calling one of these other libraries that's in, say C++, there's no way you could probably write an interface body that tells the compiler that that function you're calling in C++ is pure. I think that might be standard conforming, but there's no way for the compiler to police you and check that. So and if you look at the Fortran APIs to packages like PyTorch, you won't see the keyword pure. So right away, you can't use the intrinsic parallel features, the loop level parallelism that's built into Fortran if you're making a call into one of these other packages. So what does it look like to do inference with fiats? Well, you'll declare some neural network object. You'll invoke and infer procedure on it. We're collaborating with atmospheric scientists, so they care about things in 3D space. So you might imagine that you write some nested loop over your grid, longitude, elevation, and latitude, and you invoke this repeatedly. Now, if you're using OpenMP, which of course is the standard way to write code these days, loops are inherently sequential. And you're telling the compiler, do these iterations in this order. What has become the standard practice because parallel programming languages didn't arrive soon enough is that after we write this inherently sequential feature, we then come back and say, oops, I lied. I don't really want you to do that in parallel sequentially. I want you to do it in parallel. And oops, I wrote this nested loop, but I really want you to collapse this into one loop. Well, I think all the better to switch to part of the Fortran language, do concurrent, that first of all gives you a way to write the loop such that it is syntactically and semantically collapsed. There's no ordering implied between the iterations and between the IJ or K there. And this code can be automatically multi-threaded by a compiler, automatically offloaded, and you've now written more compact code, more portable code, because up above, I'm really only showing you what I would do to multi-thread. I believe that I'm not an OpenMP expert, but I believe that would look different and expand if you were going to offload these loops instead. As my department head, John Shelf, says, oftentimes you end up with more directives than code, or in C++, more pragmas than code. And so this way you get to write one loop. It's going to work on CPUs. It should work on GPUs. I would like to live in a world where, because our infer procedure is elemental, you could also just invoke it on the entire 3D array of objects and do all of that in one line. And if you do need OpenMP to parallelize it, then maybe you would use a work share. This syntax works even if you have OpenMP turned on, but unfortunately, at least with the compilers we've tried so far, it doesn't actually parallelize the code. So hopefully compilers will get there before too long. One of the problems is that compilers have developed a lot of great technology for supporting loops, and that's because people write a lot of loops. And why do people write a lot of loops? Because compilers have developed a lot of great technology for exploiting loops. So there's this circular issue here, which I'm hoping at some point we can break out of and get away from. This is showing what happens if you take that code with the LLVM flang compiler and running on a single CPU on the Perlmutter supercomputer here at the NERSC Supercomputer Center. And basically the ideal performance is blue. The point here isn't how close we are to ideal. The point is comparing do concurrent to OpenMP, meaning writing the explicit OpenMP. What's happening under the hood with the do concurrent is the compiler is actually converting it to OpenMP, which, by the way, isn't the only option. So another benefit here, and there are people with Flang talking about enabling you to instead convert to OpenACC. So one of the options here is you also don't tie yourself to one specific programming model. You could write one code once. You could try it with OpenMP. You could try it with OpenACC if your compiler lets you. You could also offload it to a GPU. I guess that's what OpenACC would be for. But all of these would just be with the one do concurrent that I showed you. And so this is a paper that we presented last year at the International Workshop on Computational Aspects of Deep Learning, which was held in conjunction with the International Supercomputing Conference, ISC, in Hamburg, Germany. And we were looking at using a model that our collaborator Zhe Bei here at Berkeley Lab developed for predicting aerosol transport in the atmosphere. And I don't remember which is which, but there's on one side there, you're looking at the output of per neural network, and on the other side, you're looking at the actual model. And the point is, of course, they're very close. So what about training? Well, as of, when we started writing this code a couple years back, compilers didn't have as much such great support for do concurrent, and specifically for the reduce locality in do concurrent. And we need to do parallel reductions in our code for training neural networks. And so we have three blocks. Basically, if your compiler supports Fortran 2008 do concurrent, or if it supports Fortran 2018 locality, or Fortran 2023 locality, which gives you the reduced locality. And you can basically see there the drop in complexity, the big block of code at the bottom, the smaller block in the middle, and basically one statement. I've spread it across two lines, but one statement at the top. So that's what you get in terms of compactness. The training code as a whole, I've got this big window of code in the background there just to kind of make the point that in about 96 statements, we're using what is close to state-of-the-art neural network training, or doing what is close to state-of-the-art neural network training, which is stochastic gradient descent plus the atom optimizer. And the reason we're able to do that so compactly is because we're taking advantage of the ability to write array statements and to use do concurrent. And another feature that's not used very much, well, two features that aren't used very much are the kind type parameters. So I'm just showing the syntax of what that looks like here. And I'm going to try to move towards a close pretty quickly. And the non-overridable attribute. And we actually did searches on the other deep learning libraries that are written in Fortran and didn't find this attribute anywhere. And it turns out that actually is the linchpin in order to enabling us to offload this kind of code to a GPU. So we're collaborating with compiler engineers, Karim Ergowi and Michael Clem at AMD in Germany, and they're working on being able to offload this code. They have a version of the compiler that can do some offloading, but it can't quite handle our code just yet. But that feature was added to tell the compiler, if you see this procedure call, this is the end of the road. Like there's no child type that can override this procedure. And that basically turns off dynamic dispatch. And that's which is something that you can't do on a GPU in Fortran or C++. And so that's really the linchpin in order to be able to do this, to run this code on a GPU, or will be once we're able to do so. A couple other packages I'll mention that we did, or this is not a package, but a specification that we write, the parallel runtime interface for Fortran. The basic idea here is to liberate compiler developers and their users from a specific parallel programming model, even for the SPMD features I talked about, the multi-image features. And so PRIF defines an interface which is compiler agnostic and runtime agnostic. So basically any compiler that targets this interface can use any parallel runtime library that supports this interface. So the idea is we're supporting it using GasNet EX, which is a communication library that's developed in my group here. It was invented by Dan Benachea, who's still in my group. And we're supporting it with GasNet, but there are other compilers that support these features with NPI. And people have talked about supporting these features with OpenSHMEM. You should be able to write one code once and switch between these parallel programming models just by making possibly even just a link time decision and not even having to recompile your code, certainly not having to change any of the source code. So this is just David has my slides. So this is just pointing you to a paper that we presented last year at the LLVM HPC workshop at the SC25 conference, showing some of the early results with Flang. There is a candidate release for LLVM 21, and that will be the first version of LLVM that has some of these multi-image features that I was talking about. So that should be coming out very soon, and you could start taking advantage of multi-image execution for basically any of the features that don't involve co-arrays, which actually covers a surprisingly substantial number of applications in my experience. And we support all this stuff with the runtime library, the co-array Fortran framework of efficient interfaces to network environments, so Caffeine for short. And this is a paper, this is a table from a paper that we published a couple years back at SC, and had, even at that time, most of the parallel features in the language supported. I'm just about out of time, but I cannot give a talk like this without mentioning the Fortran package manager because it has changed my life so much. Basically, just to take one example, if you look at the Fiats package, this is our build system. 3 lines, the first of which is just naming the project, and the rest are just saying our one dependency. And what's interesting is that the Fortran package manager itself is also written in Fortran. So you're seeing Fortran move into some domains that most people wouldn't imagine, and making great reductions in complexity and improvements in life if you can write a build system for your software that's this short. Moving towards conclusions, I want to conclude with a few quotes. This is from the book, from the movie Hidden Figures. There's a scene in the movie when one of the Hidden Figures, which is this was back during segregation, so it was a time when a computer was a job title. These were mathematicians, mostly held by women, and because of segregation, in this case, it was a group of Black women at NASA Langley, where, by the way, I've taught modern Fortran tutorials a couple of times, and this is one of the characters who actually was a real modeled after a real person who went to borrow a Fortran book out of the library. And she's reading the book to her son on the bus on the way back from the library and says, Fortran is a new and exciting language used by programmers to communicate with computers. It is exciting as it is the wave of the future. I'm going to say in my conclusions, I think that's still true. I think I just have 2 last slides here. I'm borrowing from Michael Pollan. He's an emeritus UC Berkeley professor who wrote several books on the food industry and summarized his philosophy of food by saying, eat food, not too much, mostly plants. He has a special definition of food, which is if your great grandparents would not recognize it as food, then it's not food. So something like Doritos, Twinkies, these are not food. I think the not too much and the mostly plant part are pretty obvious. So what I like to say about software is write software. And just like he has a special definition of food, I have a special definition of software. If you're just writing code, then it's not going to fit within my definition of software if you don't have things like correctness checks, unit tests, assertions, documentation. The not too much part is talking about the compactness that you can see was a theme in a lot of what I'm saying. And I would say write mostly pure functions. So going back to that quote from Hidden Figures, I would say Fortran 23 is a new and exciting language used by programmers to communicate with each other. We oftentimes talk about programming languages as computer languages, but if you think about it, if the only goal were to program the computer, then we could all just write assembly code and call it a day. We write source code to communicate with humans, including our future selves. So we've covered a lot of the underutilized features, and I think just about everything here I've already said, and since it's 6 minutes before the hour, I'll stop there and take questions. Thank you.
Thanks so much, Damian, for a very interesting talk. It's, I think, excited a lot of people, and it's also generated a lot of questions. So I would first ask people, I know people will have to start leaving. I would really ask everybody to consider leaving some info on our feedback survey so we can get more info about how you feel. And Damian, when you have to stop at some point, please let me know. Otherwise, we'll just continue and get through as many of these questions as we can and try to answer the rest offline.
Cool.
So,
I think I have a meeting right. I have a meeting right after this with 2 people who I think are here, so so I'm safe.
So we'll just keep them here and
Yeah.
call it another meeting. All right. So the first question is object-based the same as object-oriented?
So as I was saying, it's a term that you'll sometimes see as basically object-oriented programming minus whatever the thing you think is the most important part of object-oriented programming, which usually is inheritance. So Fortran 90 had object-based programming because it didn't have inheritance, which we call type extension. And then Fortran 2003 was the first language that was really object-oriented programming.
All right, and then is Fortran 90 and later versions made to be more like other object-oriented programming languages like C++? If so, why use Fortran and not just some other OO language? Is the reason to be able to run old Fortran codes? I assume one reason to use
Oh
Fortran
boy.
90 is that it's fast.
Sure. I mean, I hope my whole talk was an answer to that question. I showed you how you can write an elemental procedure and basically have the compiler generate the other 45 instances of that procedure that you would have written if you didn't have the elemental feature. And Mike Carew helped me with a practice talk along with David and Ruben a couple weeks back preparing for this. And at the time, Mike initially thought that there might be something in C++ analogous to elemental, but then went off and researched it and came back and said, no, I don't think there's anything analogous to elemental in C++. So there's lots of reasons to write Fortran independent of legacy code. There are really, to me, exciting new features that are exciting people across the age range, by the way. I've had people in my group who are in high school who are excited about what we're doing with Fortran. Specifically, one high school student has now come back to me in college and I'm about to appoint him as an affiliate in my group because he wants to work on our deep learning library. So there's lots of cool stuff.
Yeah, definitely. What practical steps can the community take to get compiler developers to put more time and urgency into implementing the full Fortran standard and fixing all bugs? It feels slow right now.
So I believe the Fortran community has a certain amount of PTSD because, Fortran 2003 basically broke the compiler community's back in a sense. It took some compilers a decade or so. In fact, I talked about all the bug reports that I'm submitting. On one compiler, I submitted 18 bug reports just in the months of October and November last year. And I'm still submitting bug reports to that compiler just on a feature that was in Fortran 2003. So I get it. I feel your pain. But what I would say is we're in a better place now. I actually taught a short course in the year 2018, and the title of it was Writing Fortran 2018 Today, because I wanted to make the point that there was a lot of aspects of the language that you could already begin using with several compilers. And what I would say is now I know of at least 3 compilers. Let's see, the Cray compiler is 2023 compliant. The Intel compiler is 2023 compliant. And I would say, at least for my purposes, everything I care about personally, currently from 2023 is supported by G-Fortran, Flang, the LLVM Flang compiler. I'm sorry, yeah, and the numerical algorithms group compiler, NAG. So those are kind of like a leadership group that's really trying to keep up with the standards, and you can really dive in. And you will also, and as I said, 1 bug report a week on average since the beginning of 2024, and only 1 of those on Flang, LLVM Flang. So the one issue I see right now with LLVM Flang is it's not yet generating fast enough code in many cases. And I know that's obviously important to people, but at least in terms of feature support, it is the most robust and feature complete compiler that I use.
All right, next question. Given that the features you're highlighting are relatively unknown, have you found that AI is able to effectively use them in generated code? Have you considered developing a Fortran MCP?
I've been very surprised in that regard. What I will say is that, so yes, the AI is able to generate fairly modern code using things like do concurrent and, I think possibly even, we didn't try reduced locality, but, the number one thing I would say though is I think the AI is good in the hands of someone who could have written the algorithm themselves. You really do have to be able to check it. I wrote one paper last year that unfortunately didn't get accepted. We're looking to revise that soon. But basically, we tried 4 different AI models. And for a problem where we were only asking for about 40 lines of code doing central differences for the heat equation, for the Laplacian operator. So the kind of stuff that a first year or second year grad student would know. And of the 4 models, we could only get one that could even give us compilable code. And the great news is we gave it 3 tests, and it did pass 2 out of 3 of our tests on the first pass, but with a certain way that we were doing the prompting using Julienne tests for the prompts. And but then there was a regression on the second iteration. It passed only 1 test out of 3. So they can't get you all the way there, in my view, in terms of correctness. But yes, they do know about the more recent features and can make use of them.
With so many compiler bugs you're submitting, how are you able to reliably run your code in production?
So flang. I I do the vast majority. I really do all of my development with flang. And then because I know that not many people are using flang yet, I then switch to other compilers. Fortunately, my group member Dan Bertocea has done an awesome job of putting together CI testing, where we will have 25 combinations of compiler version, operating system. And so basically I do all of my development with flang because I can move fast, get things done. Then I start checking other compilers, and I submit bug report after bug report after bug report after bug report, and work around them. So I've only run into one case so far where there was just a deal breaker, and that's the one where I'm submitting so many bug reports now. Basically, the parameterized derived type support in G-Fortran was fundamentally broken, but there's a developer, a really sharp physicist, Paul Thomas in the UK, who's working on fixing that. And the next G-Fortran release will have much more robust support, at least for kind type parameters.
So I'm going to skip a question here that I think you've answered repeatedly during the presentation. What's the fault model for multiple images and/or co-array programming?
Oh, that's interesting. Not something you hear a lot about these days. So the basic idea, so we have the ability to detect failed images, and you can collect images into teams, as I mentioned. And what you could do, for example, is collect all of the failed images into a team. That way they don't affect the rest of your computation. That's a very minimalistic technology. You'll still need to figure out some kind of checkpoint restarting, or maybe neighboring images can share copies of each other's data, but it can at least give you the ability to continue in the face of failure. That fault tolerance is something that was talked about quite a lot, 5 or 10 years ago. You really don't hear much about it these days. And my group member Dan Bertocea could speak to this more in greater detail if he's with us. But we're planning fairly minimal support for that because, first of all, there doesn't seem to be a lot of demand, and we don't think there are great ways to implement those features. And Dan can correct me if I'm wrong.
We'll assume silence is consent. So another question. At my organization, we get frequent requests from management to consider translating our million lines of code from Fortran to some other language, C++, Python, whatever. Some reasons are GPU porting performance, possibly declining support for Fortran compilers, and attracting software engineers. How do you respond to this?
Okay, declining support from compilers. What's happening is that the compiler world is converging. Basically, AMD contributes to Flang. They have their own fork of Flang, but I've actually talked to them about their intentions. Anything they develop on their fork is basically a staging ground. They intend to push it all out to the central LLVM repository as open source. NVIDIA wrote most of Flang. In fact, as of a couple of years ago, there was one compiler engineer at NVIDIA who had written over half of Flang. ARM contributes to Flang. And even, I guess, it's companies like Intel or HPE, they're using the LLVM backend, which kind of gives you an idea that the whole world is kind of coalescing around this one compiler. So I think that addresses the compiler question to some extent. And as far as recruiting young developers, that is the biggest challenge. And one of the problems is that universities aren't teaching Fortran at all anymore. So I don't know that I have a great way to solve that, other than that we need to keep growing the grassroots efforts. There's a great Fortran discourse community where you'll encounter people across the age ranges who are doing awesome things with open source Fortran. And I'm giving a talk in March at Los Alamos, many of you might have heard about the report that Los Alamos published a couple years back on the risks of continuing to maintain Fortran. So of course, the title of my talk will be The Risks of Abandoning Fortran. I'm fighting the good fight. And if you look at the data, if you look at what's happening on the big platforms like Perlmutter here at NERSC, a very significant fraction of the cycles are still Fortran codes, probably close to half on Perlmutter from data that I saw from several years back. I've seen data on supercomputing centers in the UK where it's more like 80 or 90%. So, when I talk about how computer programming languages are human languages, that's a point that has really important implications, even at a sociological perspective. I actually wrote a short position paper with an linguistics professor at NYU, Renee Blake, talking about language discrimination. I know that's an incendiary comment, especially in the current times. But if you just think about it, it's almost obvious that if these really are human languages, right? I mean, why are we having the AI generate high-level source code? Why not just have the AI generate assembly? Okay, because we want humans to understand it. These are human languages. So of course, biases are going to crop up in this human language, just like biases crop up in other human languages or dialects or what have you. So, let's just say the history of trying to stamp out human languages is not a great history, so I think I addressed a couple of the points there, but I think there were three and I forget what the first one was.
Yeah, it had to do with GPU porting and performance concerns.
So again, we're in a new place. The compilers that can automatically offload do concurrent are NVIDIA, HPE, Intel, and as I said, it's under development for LLVM flang. I suspect that by the end of the year, I'm not the person doing it, so take this as complete speculation, but I suspect that later this year we'll see automatic offloading to GPUs of do concurrent in LLVM flang. So if the motivation is GPUs, do you want to have to choose between OpenACC or OpenMP or CUDA, or do you want to just write your code once, change a compile time flag, and make that decision then, right? Do you want to have to write more code? You're going to have to write all the directives for OpenMP or OpenACC or what have you. And so I really think if GPUs are the motivation, if you look at where we are now in compiler technology and especially where we will be soon, I think the best argument is to stick with Fortran.
All right, we still have a bunch more questions. Some of them are more detailed, and I think, given the time, I think I want to wrap up with this one. How do we learn about all this stuff? I try to keep up on the Fortran language, but a lot of this stuff is completely new to me. Are there textbooks or something?
That is a really tough one. So I wrote the foreword for a book by Milan Churchick. He's a CURCIC. He's a professor at the University of Miami. It's called Modern Fortran. That's one of the more recent ones, but even that one is about 3 to 4 years old now. And I published a book myself in 2011 on Cambridge University Press. It's called Scientific Software Design, the Object-Oriented Way. There's actually a lot of Fortran and C++ in that book, so it's kind of a good Rosetta Stone if you're looking for one. And even though that book was published before there were Fortran 2008 compilers, and even back then there wasn't great support for 2003, we tried to write it in a forward-looking way. So it really uses heavily object-oriented Fortran 2003, and at the end of the book we even have some parallel Fortran 2008 in there. I really, really passionately want to write another book, but I also want to develop a lot of code that I can then use to work out the ideas that I have. And I think I'm close. In fact, my New Year's resolution is not to launch any new software projects. I told you this, we just have one that came out a week ago, and it's one of the things I'm most excited about in my whole career. So I want to build on what we have and get to the point where I can write another book. But if nothing else, take a look at the projects that I told you and reach out to us. Start writing unit tests. There's a philosophy of test-driven development. Write your tests before you write your code. And if you're doing that with Julienne, you'll be using very modern Fortran. And you can start to dive in and see how the test suite is written in Julienne and see how Julienne itself is written. And that can help be your guide, and we'll be glad to help out.
And also, there's a tradition in the Fortran community of papers that summarize the new features as each standard is released, right? That Metcalf
So
has been the
typically,
lead author. John
uh,
Reed.
yeah, so John Reed is typically the lead author on that, and every time there's a standard, he publishes a new article. And John is still active on the committee, and he did write one for Fortran 2023. I imagine he'll write one for Fortran 2028, hopefully. But he's up to date. His latest version covers the most recent standard.
Yeah. All right. So there are additional questions, and I appreciate everybody who submitted questions. And unfortunately, we haven't had time to go through all of them. I think we could probably spend another hour at it, but I'm going to ask Damian to look over these and provide some answers offline, and we'll publish these along with the slides and the recording. And everybody who registered will get an email when those are available. If you snuck in without registering, just go ahead and monitor the website, and they'll be posted. Links will be posted there. And with that, oh, he's looking
I
for
was,
a reference list.
yeah, I was trying to see if I had. Oh yeah, so I mentioned two books. I mentioned Milan Turchik, so that's his book, Modern Fortran, and then I mentioned my book, Scientific Software Design. So those are a couple places you could start.
Yeah, that's great. So thank you very much, Damian. We'll look forward to maybe another presentation, especially if we get a lot of good feedback from people. And thank you all for attending and the great questions.
Thank you. Bye-bye.
Bye.